Well, here we have another reaction rate problem, and it involves nitric oxide. That's its old name. It really should be called nitrogen monoxide, indicating that we have just one oxygen. There's a dioxide, there's even a dinitrogen monoxide. So there are a lot of nitrogen oxides. This one's really unusual because it's got an odd number of electrons. It's got this lone electron out here, so it's ready to bond things. It's what they refer to as a radical. And it's a gas. And let me pull up the web page for it, the Wikipedia page, which is interesting. Again, they've got different types of Lewis dot diagrams, and they're really not adequate for explaining this molecular structure. But they do indicate that here's one of the ways it's shown easily just using the Lewis dot system. It's an important intermediate. It's used to make other things. It's generated and then it's used in a reaction mechanism. And in fact, they refer to it as a heteronuclear. So it's got two different atoms, even though it's diatomic. So it's got two atoms, diatomic, but they're different. They're very similar. Nitrogen and oxygen are next to one another on the periodic table. So it's an interesting compound. There's been a lot of research in it because you actually make nitrogen monoxide, and it's used to affect how your vascular system, it controls the dilation and constriction of blood vessels. It's very, very important in cardiac function, and there's been a lot of research done on it as a result. In fact, this is a better description of it in terms of molecular orbitals, in terms of how they explain its operation. But we're not going to get into that. That's graduate level work. We're going to just find out experimentally what's happening with it. And our task is to find out how quickly it reacts with oxygen. Here's our reaction. We want to know how quickly it reacts. In fact, here's the study. Two NOs make two NO2s. And if you start off experimentally with a certain amount of NO, and they detect it using fluorescent technology, if you have a 0.0182 molar, now they could have used atmospheres here because we're dealing with gases, and this is your concentration of oxygen around it, a little bit higher. This is how quickly you make the NO2 and how quickly the NO disappears, and the oxygen will disappear half as quickly because of our coefficients and stoichiometry. But this is how quickly the reaction occurs, where it gets 0.00533 molar per second. So it's like instantaneous in terms of its reaction. And they've done a trial with different reactions. And again, if we're going to be examining this in terms of the rates of reaction here. So I sort of simplified the rates by changing them to 5.35, 21.4, and 2.67. And with these rates, always check to see if there seems to be multiples. Like here, this 2.67 is half that of the 5.35. And here you can see 0.0113 is half of 0.226. So sort of look at the numbers for possible multiples. Because in the end, the first thing that's going to be asked is, what is the actual equation that describes how quickly this reaction goes? I mean, that's a powerful equation. The rate law expression. Expression would be the equation. And notice I put question marks, not because of the concentration of the NO and the O2, but in figuring out this equation, these question marks are exponents, and they're almost always 0, 1, or 2. Occasionally, very occasionally, you'll have a fraction or even a negative value. But in almost every case, this is either going to be a 0, 1, or 2. In fact, if you have to quickly answer a question, I would say the rate is equal to K NO1, 1. I mean, you'd have a chance of having it right. But let's not take a guess. Let's find out what these values are. Do so pretty quickly. What we're going to do first is we're going to examine just the NO. We're going to try and figure out how important the concentration of the nitrogen monoxide is. And so let me scroll up a bit. I've taken a case where we've changed the nitrogen monoxide. Here is the NO, 0.0182 and 0.0364. Now notice it's a double. So you know the concentration of the NO went up times 2. Let me write this down. Between trial 1 and 2, we had a doubling. I'll put that X2 written down, where we made the concentration of the NO twice as high. Now, if NO was useless in this reaction in terms of the speed, we would have no change in the rate, and it would be a NO raised to the 0 power. But notice the rate changed. And again, looking at this 0.0535 and this, it's a little bit easier to look at my numbers. The concentration, notice the O2 didn't change. That's important because we don't want to get the O2 involved in this. We're just dealing with the NO. So this is good that they didn't change the O2. Now, notice the concentration, obviously not the concentration, the rate, the molar per second that the NO is produced is not double. It's 5.35 to 21.4. It went up a lot more than times 2. And in fact, let me pull up my calculator. And I'm going to take that 21.4, 21.4, and divide it by the 5.35, because I want to see how many times faster it went. I know the concentration was times 2, and the rate went up times 4. So the rate increased by 4 times. So that's sort of funny. If you double the concentration of the nitrogen monoxide, this goes up 4 times as much. So if NO is twice, our rate goes up by 4. Well, how do we take care of that? We just simply say then the NO is going to be important by its square. If you square the concentration change of the NO, that's how it's going to affect the rate. If we had tripled the nitrogen monoxide, the rate would have gone up 9 times. So this, slight changes in NO are to make huge changes in how quickly things react. So we've come up with that part of the rate law expression. We've found out that the exponent for the NO, which I said will be a 0, 1, or a 2, almost all cases, is a 2. We've got half the problem. The rate of the reaction is equal to a constant times the concentration of the NO squared, and then we're going to come up with the rest of this. We're going to figure out the oxygen and its exponent. So let's go to another trial. In this case, I'm using trials 1 and 3. 1 as a 0.0182 for nitrogen monoxide and 3 for 0.0182. So we didn't change the nitrogen monoxide. We only changed the O2. And again, let's see how it changed the rate. Notice that this 0.0226, 0.0113, no coincidence, they cut the concentration in half. So I'm going to write that down. The concentration was cut in half. I'll write that right there. And now let's see what happened to the rate, 0.0535. And again, it's easier to look at these numbers, and you might be able to see the half. If not, let's just get our calculator out and see what 2.67 divided by 5.35 is. 0.4999. That's half too. So the rate decreased by a half. That's directly proportional. So therefore, we can figure out that question mark. We would know that the importance of the oxygen is to the first power. If you double the concentration of the oxygen, you double the rate. If you half the concentration of the oxygen, you half the rate. Let me change the font size here to a subscript size. I'll make it a 12. and that looks good. This is now our rate law. We know the rate of this reaction is going to be equal to a constant, which we're going to figure out next, times whatever the NO is squared, times the O2 raised to the first power. This is a lot of question, but let's now see what this K is, because we can solve for it because we have data. We know what the rate is, we know the NO, we know the O2, and K is solvable. This is a very, very important value. So let's get the calculator and do that calculation. And let's use the same calculation we had here. Let's use this data. We could use trial 1, or I'm going to use 3 just for fun. I'm going to say my rate, that's what I'm going to use here. I'm going to have 0.0267. I know what that is. That's my rate. And I know the NO and O2, and I'm solving for K, so I'll divide by the concentration of the NO2, which is 0.0113 squared. Got a convenient squared there. And I'm also going to divide then by the O2 raised to the first power, but who's going to raise it to the first? 0.0267. And that's going to give us our constant. I'm going to double check. 0.067, 0.0113, 0. Oh, this is wrong. It's a good thing I checked that out, because I'm dividing by the concentration of this is all messed up. It's a good thing I checked this, because I really should be dividing by the concentration of the NO, which is 182 squared, and then the concentration of the oxygen, which is the 0.0113. Now I'll double check. The rate, 0.0267, divided by 0.0182 squared, divided by 0.0113. Let's do an enter. And we get a big number. This is a fast reaction. In 1 second, we were lost, in less than 1 second, we would have lost all of our NO. So we now know what the constant is. I mean, we've got this thing figured out. I did the solution, I used these numbers, and now I can say this is what the constant is. In fact, let me pull that calculator up again, and it's 7,130. I'll get my text going and get it back up to 18 size and write down 7,130 is, double check. Yep, 3 significant figures. Now, you get 1 point for calculating the K. You also get 1 point for the right unit. Now, when you're calculating K, you're dividing M by M, so M disappears because the rate is molar per second. But you're also divided by molar squared, so your denominator is going to be molar squared per second. And you can write it either one of these ways. I usually rate people like to use exponents, so we will have our 7,130, and again, a weird unit, but it's one that works. If you then multiply this unit by K, you get molar per second as your final result. So we've found our K. We've got this equation all figured out. I could say rate is equal to 7,130 times the nitrogen monoxide squared times the oxygen concentration squared. Beautiful. Well, let's check it out. I've got my calculator, and let's take this data that we have for trial 1, because we didn't use trial 1 in this calculation. We used trial 3, and see if we get this rate. I'm going to take and use this equation, K, which I have there. So I'm just going to multiply my constant, which I had last time, times my 0.0182 squared. So I'm taking my concentration of my nitrogen monoxide times my constant, of course I'm squaring this value, times the concentration here, 0.0226. I gotta double check. You hate to do the calculation because you put a number in incorrectly. Now we should be getting 0.0535 molar per second. Let's see if we get that, if this matches it. If it does, we know our equation's right. So this is, ta-da, enter 0.0534, 0.0535. Close enough, especially experimentally. So we must have the right equation because we put these numbers in to the equation and got the correct rate. So there we have it. This is rate laws. Now, chemists are supposed to know about changes. Now, we know about changes in terms of balancing reactions and stoichiometry, but now you even know how quickly things can happen. With that equation, this rate law, squared to the first power and the constant, at this temperature, you will know how quickly this nitrogen monoxide will react with oxygen to become our nitrogen dioxide. You're a real chemist if you can figure this out. Bye.